In this section, we talk about inverse functions. So when we talk about inverse function, we talk about one-to-one functions, and then we define the inverse function, and we use equations of inverses. So let's start with explaining what do we mean by one-to-one function, and then we'll talk about the relationship between one-to-one functions and inverse function, or why do we need to study one-to-one functions. So let's start with the following relation x. This is set x and this is set y. So we have some numbers, some values in the set x and some values in the set y. Now -2 is associated with 2, -1 is related to 1, 0 is 0, 1 with 3, 2 with 5. So in this case, each x value corresponds to only one y value. So for example, -2 corresponds to 2, and -1 to 1, and so on. So each x value corresponds to only one y value. So this is what we mean by one-to-one relationship or relation or one-to-one function. So this is some relation between x and y. F is a relation, and we know that functions are special cases of relations. So this relation is one-to-one. Now, what do we mean by one-to-one function algebraically? Algebraically, if you give me two different inputs, then the outputs will be also different. So different inputs, I mean a and b are from the set x, and f of a, f of b are from set y. So different inputs like these, -2 and 0 are different inputs, and they give us different outputs. So different inputs correspond to different outputs. For example, this is one of the examples, the previous one, and look at the following function f. We have 1, 2, 3, 4, 5, some values in x, and 6, 7, 8, 9, some values in y, and the 1 is related to 6, 2 corresponds to 7, 3 corresponds to 7 as well, 4 to 8, and 5 corresponds to 9. This relation, this function, is not one-to-one, because as you can see here, 2 is related to 7, and 3 is related to 7 as well. So both of them are related to same value. So two inputs give us one output. That means this is not one-to-one correspondence, or not one-to-one function, sorry. So this is not 1-to-1. Now 2 is different from 3, two different outputs. They give us f of 2 is equal to f of 3. F of 2 is 7 and f of 3 is 7 as well. So that means not 1-to-1. Equivalently, we can write it this way. If the images are, or the outputs are the same, then the inputs are the same. And in most of the cases we use this one because those are equivalent. This is equivalent to this. You may start with different inputs and then you get different outputs, or you start with same outputs and you get same inputs. This is called contrapositive. I mean, those two statements are equivalent, but this is contrapositive of this. Now let's take some examples. We want to show that f of x, the function f of x, equals 2x plus 1 is a one-to-one function. Now, in order to do this, we want to do this example by two ways. We want to show this algebraically and then graphically. So let's start by showing this algebraically. So algebraically, I mean by algebraically is to use this formula or this way of proving one-to-one functions. The relation is 1-to-1. So f of a equals f of b. So we start with the left-hand side, f of a equals f of b, and we start solving, and then the equation, the resulting equation, to get a equals b. If we get a equals b, that means they are the function is 1-to-1. So what is f of a? F of x is this, 2x plus 1. So we substitute a, we get 2a plus 1. And substitute b, you get 2b plus 1. Those should be equal. And then we solve for, we want to show a equals b. So let's subtract 1 first. So we get 2a equals 2b, and then you divide by the coefficient of a and b, which is 2. So we get a equals b. So we started with f of a equals f of b, two equal outputs, and we obtained two equal inputs, and according to this, the function is 1-to-1. Now let's show this graphically. Now graphically, that means we apply the horizontal line test. The horizontal line test says every horizontal line, or any horizontal line, let's use the word every has horizontal line must intersect the graph in at most one point. So if we graph horizontal line, then that line will intersect the graph in at most one point. So let's graph this function. The function is f of x equals 2x plus 1. So if we take x equals 0, we get y equals 1. if we take x equals -1/2, we get y equals 0. That's the x-intercept. So this is the graph of 2x plus 1. It's linear, increasing. So if you try any horizontal test, any horizontal line, I mean using horizontal line test, this curve or this function, this graph of function will pass the horizontal line test. Passes the horizontal line test, and that means yes, it is one-to-one. One-to-one function. So this is how we show it graphically. If we are given some graph, we can show that the function is one-to-one. Okay. Let's take another example. If we have f of x equals square root 25 minus x squared, we want to show that, or to check if f of x is one-to-one. Okay, so to do so, we start with f of a equals f of b. So f of a equals f of b, and want a equals b. So f of a equals f of b, substitute a, you get square root 25 minus a squared equals square root 25 minus b squared. And then we square both sides. So we square both sides. We get, when we square, by that we get rid of the square root. So we get 25 minus a squared equals 25 minus b squared. And then we subtract 25 from both sides. So we have negative a squared equals negative b squared. So a, we can drop the negative sign from both sides, and then solve for a. So a is plus or minus square root b squared, and that's plus or minus absolute value of b, and that's equal to, because we cancel the square with the square root, and we get absolute value of b, and that's plus or minus b. So one value a give us two values here, b or negative b. So that means it's not a one-to-one function. Maybe it's easier to check some values. If you find another way, and easier actually, if you just show that this is not satisfied for specific value. If you choose some values, like take some value for a, some value for b, let's take a equals 3 and b equals negative 3. Those are different. So we started with a not equal to b, 3 not equal to negative 3, and we want to show, this is the other formula, f of a is different from f of b. If those are not equal, then the images, the inputs are not equal, the images should be not equal. So when we have 3 and negative 3, now substitute them here, f of 3 and here f of negative 3. We want to see if they are different. If they are different, then this is one-to-one. So we have square root 25 minus 3 squared, square root 25 minus negative 3 squared. This is 25 minus 9. This is 25 minus 9 as well. So this is square root 16. This is square root 16. That's equal to 4. 4 equals 4. We didn't get inequality. We didn't get them not equal. So that means this is not one-to-one. Some people prefer to write it this way. So this is not one-to-one. Okay, now let's take another example. if f of x equals x squared plus 1. Now, let's graph this function. So we know that the graph of x squared is this. If you remember from previous video, this is x squared. And then when we add 1, that means we make a shift up by 1 unit. So this is x squared plus 1. Now, if we look at this graph, you can try the horizontal line test. As you can see, the horizontal line intersects the function at 2 points. So this fails to pass the horizontal line test. So it's not 1-to-1. Okay. Now, keeping this in mind, we can move to the inverse functions. Inverse functions. Now let f of x be a 1-to-1 function. So this is very important. The function should be 1-to-1. Then g of x, another function, is an inverse, or is the inverse of f of x if the following two conditions are satisfied. F compose g of x is equal to the identity x, and g compose f of x gives x. If those two conditions are satisfied, then we say that g is the inverse of f. Now let's take an example. If f of x equals x cubed minus 1, we want to find or show that the function g of x equals cube root of x plus 1 is the inverse of f of x. Now, to do so, we first need to check if f is 1-to-1. So this is f. Let's do this graphically. What is the graph? How the graph of x cubed minus 1 look like? Let's start with the basic function. The basic function is x cubed. This is x cubed. Now x cubed minus 1, that means we shift this down 1 unit. So we get this is x cubed minus 1. If we look at this function, the graph looks like this. I'm sorry about this. The graph looks like this. This is x cubed. And now what is how the graph of x cubed minus 1 looks like? We make shift down by 1 unit. So the graph looks like this. This is 1, the x-intercept. Is 1, 0. So it intersects the x-axis at 1. So this is x cubed minus 1. So as you can see, it's shift down with 1 unit by 1 unit. Now if you try the horizontal line tests, the horizontal line intersects the graph in at most 1 point. As you can see, every horizontal line intersects the curve of x cubed minus 1 in at most 1 point. So this is 1-to-1 function. Good. If it's 1-to-1 function, we only need to check those two conditions. So we want to show that first f circle g of x, which is equal to f of g of x equals x. So let's substitute this. We have f of, what is g of x? G of x is the cube root of x plus 1, and then we plug this into the function f. The function f is x cubed minus 1, but instead of x we have cube root of x plus 1. Then we simplify, we can cancel 3 with cube root of x plus 1, so we get x plus 1 minus 1, and that is equal to x. So the first condition is satisfied. Let's do the second condition. G circle f of x. So to G compose f of x, or G after f of x. This is G of f of x. This is equal to G of what? F of x is x cubed minus 1. And then we substitute this into the function g. The function g is the cube root of x plus 1. X, in this case, we need to replace it with x cubed minus 1. Now we simplify, we get cube root of x cubed minus 1 plus 1, and that is cube root of x cubed, and then we just cancel 3 with cube root, and we get x. So the second condition is satisfied as well. That means, so G is the inverse of f. Now, how to find the inverse? Now we learned how to check if a given function is inverse to another function. Now, how to find the inverse of a function? Before I start, I want to start with a notation. The inverse of f, for example, the inverse of the function f of x is denoted as f negative 1 of x. This is not negative 1 actually. We write it as negative 1, f negative 1 of x, but it's read the inverse of f of x, or inverse function of x, of f of x, or inverse, or f inverse. We can write it, we can read it as f inverse. That means the inverse of the function f. Now, just a word of caution, you need to remember that f inverse of x is not equal to 1 over f of x, because this is not negative 1. This is just a simple, or something that shows us that we have inverse of a function. So don't confuse f inverse with 1 over f. Those are completely different. So f inverse just denotes the inverse of a given function. Good. So this is the first point I want you guys to remember. Now, how to find the inverse of a given function? Let's take an example. If we are given f of x equals 2x minus 5, we want to find f inverse of x, the inverse of f of x. Now, how to find the inverse of the function f of x? First, we need to check if f of x is 1 to 1, because if it's not 1 to 1, we can't find the inverse. So the function f of x 2x minus 5 can be graphed. When we substitute x equals 0, we get negative 5 here. Substitute, for example, 5 over 2, 2.5. You get 0. So the graph looks like this. It's increasing function. That means it's 1-to-1. If you try the horizontal line test, it passes the horizontal line test because every horizontal line must intersect the graph in at most one point. So the function is 1-to-1. Now we can find the inverse. How to find the inverse? The first step is to write the function as an equation. As an equation, I mean to write it this way: y equals f of x. So when y equals f of x, this becomes y equals 2x minus 5. And then the second step is to interchange x and y. So y becomes x and x becomes y. And then third step, solve for y. Now to solve for y, we add, let me rewrite it here, x equals 2y minus 5. So we add 5. We get x plus 5 equals 2y, and then we divide by the coefficient of y. So y equals x plus 5 over 2. And then the last step is to replace y with f inverse. Replace y with f inverse of x. So this becomes f inverse of x equals x plus 5 over 2. And you can check, this is the inverse of f of x equals 2x minus 5. If you want to check, you use or you try to apply those two conditions. If they are satisfied, then the answer is correct. Now, what is the relationship between domain and range of the function, original function, and the domain and range of the inverse? Now, domain of f of x is the same as the range of f inverse of x. The range of f of x is the same as the domain of f of x. Because as you can see, if this is x, this is y, this is domain, and this is the range of the function f. So as you can see, this is the domain and this is the range. Now if you find the inverse is starts at y and ends at x. So this is f inverse. The domain here is y and the range is x. Okay. Now let's take an example, another example on the inverse of a function. If the relation f is given by 2, 1, 0, 3, 3, 2, 4, 0, we want to find f inverse. First, this is 1-to-1 because as you can see, any two different inputs give different outputs. So this is 1-to-1. And then we find the inverse. The inverse can be obtained by just reversing the order. 2, 1 becomes 1, 2. 0, 3 becomes 3, 0. 3, 2 becomes 2, 3. And 4, 0 becomes 0, 4. What is the domain? What is domain of f? Domain of f is the x coordinate. So the domain is 2, 0, 3, and 4. What is the range of f? range of f is 1, 3, 2, 0. The y coordinate 1, 3, 2, 0. Now, what is domain of f inverse? Domain of f inverse is 1, 3, 2, 0. 1, 3, 2, 0. And what is the range of f inverse? Range of f inverse is 2, 0, 3, and 4. So 2, 0, 3, and 4. Now let's compare those. The domain of f is the same as the range of f inverse, and the range of f is the same as the domain of f inverse. Now let's take another example. If f of x is equal to x minus 2 raised to the power 3, we want to find f inverse of x, the inverse of this function. So to do so, let's first show that the function is 1-to-1. F is 1-to-1. We can show this by graphing the function. Now, what is the basic function? The basic function is x cubed. This is the basic function, x cubed. But we have -2 subtracted from the variable, not from the whole expression. So it's subtracted from 2. That means we make a shift to the right by 2 units. So if we make a shift by 2 units, we get this graph. So at 2, we have x-intercept at 2, 0. Okay, now we still have a function, a one-to-one function, because every horizontal line can intersect the graph, or must intersect the graph at most one point, so it passes the horizontal line test. Okay, now we find the inverse. We apply the previous 4 steps. So the first step is to find f inverse of x. The first step is to write y equals, instead of f of x, we write y. Y equals x minus 2 raised to power 3. Second step, interchange x and y. So this becomes x and this becomes y. The third step is to solve for y. To solve for y, we start by taking the cube root of both sides in order to get rid of cube here, because we're solving for y. And then we simplify. As you can see, we can cancel 3 with cube root of the cube root. So we get cube root x equals y minus 2. And the final step is to add 2 in order to write y, to isolate y. So this is cube root of x plus 2. Now the last step is to replace y with f inverse of x. So we get this function. This is the inverse of the function f of x equals x minus 2 all cube. Okay, now by looking at this, if we are interested in finding the domain, what is the domain of this function? The domain of this function f of x is all real numbers, so negative infinity to infinity. The range is the same, from negative infinity to positive infinity, and that's correct for f inverse, because this is cube root, not square root, not even root. so we don't have any problem here with values of x. Okay, let's take another example. So if f of x equals x squared plus 2, can we find f inverse of x? Let's see. We need to check first if f of x is 1-to-1. Let's see. Now let's graph this function. So the basic function is x squared. So the graph of this looks like this. This is x squared. And then when we add 2 to the whole function, basic function, that means we make shift up by 2 units. So the graph looks like this, x squared plus 2, the blue curve. So if you try any horizontal line or try some horizontal lines, you find that this horizontal line intersects the graph in 2 points, not in 1 point. So it does not pass the horizontal line test. So it's not 1-to-1. So no inverse. We can't find the inverse of this function. But what can we do in this case? If we want to find the inverse and this function is not 1-to-1, what can we do? But we can restrict the domain. We can restrict the domain on some interval where the function is 1-to-1. On some interval where the function is 1-to-1. For example, for this function, if we just choose, let me graph this function again. This is x squared, sorry. Now this is x squared plus 2, and this is not 1-to-1 function, but if we restrict the domain on this part, on this interval, just the positive part of the function, we find that we have this curve, and this curve is 1-to-1, because if you choose any horizontal line, it will intersect the graph, this graph, in at most 1 point. So we restricted the domain. That means we chose some part of the domain, I mean some part of the x-axis where the function is 1-to-1. The function is 1-to-1 on this part from 0 to infinity. So if we restrict the domain on some interval where the function is 1-to-1, then we can find the inverse. So we can define the function f of x equals x squared plus 2, where x, now we should restrict it here, where x belongs to 0 to infinity. This is red, belongs, this symbol denotes belonging to. So belongs to the interval 0 infinity. So we can't accept negative values for x because we want the function to be 1-to-1. Okay, so after restricting the domain, we can find the inverse. So we apply same steps. So first y equals x squared plus 2. We write it as an equation. And then, rather than writing it as a function, f of x. Okay, so the second step is to interchange x and y. And then the third step is to solve for y. So subtract 2 from here, so you get y squared equals x minus 2, and then take square root, you get square root x minus 2. You get plus or minus, but since this is y is positive, as you can see, it's above the x-axis, it's positive, it cannot take negative values. So we only choose the positive case, x minus 2, because y represents the height of the function, so this is positive. So, and then the fourth step is to replace y with f inverse. So f inverse of x is square root x minus 2. This is the inverse on the restricted domain. Okay, so what is domain of f inverse of x? Domain of f inverse of x is the values where the inner function is non-negative. So we want x minus 2 to be greater than or equal to 0, because even roots or square root is not defined for negative values. So x is greater than or equal to 2. So from 2 to infinity. This is domain of f inverse. Domain of f inverse is the range of f. And as we can see, this is f, this is the function f, and the range is from 2 to infinity. From 2 to infinity. So this is equal to the range of f. Okay. One more example. Now, if we have a function like a rational function like 2x plus 3 over x minus 4, where x is not equal to 4, because if x equals 4, that means the denominator is equal 0, and that's not defined. Now, what is domain of this function? Domain of f is everything except 4. So everything here and here, except, everything except 4. So it's negative infinity to 4 union 4 to infinity. Good. So this is the domain of the function f. Now, if I ask you to find the range of this function, it's not easy to do so, because then you need to graph this function, and it's not easy to graph this function. But to find the range of this function, you can find the inverse of this function, and then you find the domain. It's very easy to find the domain of a given function. So if you find the domain of the inverse, that's the range of the original function f. So let's find the inverse function of f. So first we write y equals 2x plus 3 over x minus 4. And second step is to interchange x and y. And the third step is to solve for y. So we can multiply this by this. We have x times y minus 4 equals 2y plus 3 times 1. Now we distribute x on this expression. So xy minus 4x equals 2y plus 3. We are solving for y. So we have 2y here and xy here. So let's bring this here. Becomes xy minus 2y. And this, let's bring this to the right hand side. We have 4x, positive 4x plus 3. And then we can take y as a common factor. So y times x minus 2 equals 4x plus 3. Then the last step is to divide by x minus 2. So the function y equals 4x plus 3 over x minus 2. And then the fourth step is to replace y with f inverse of x. So 4x plus 3 over x minus 2. Now what is the domain of this? X is not equal to 2, because if x equals 2, then we get 0 in the denominator, and that's not defined. So what is domain of f inverse of x? The domain is everything on the real line except 2. So negative infinity to 2 union 2 to infinity. So since this is the domain of f inverse, this is equivalent to range of f of x. So from this function, it's not easy to find the range. But after finding the inverse of the function, the domain of the inverse function is the same as the range of the original function.